we can have everybody up. And we're going to go ahead and do our chapter 8, goal 2, chapter 8, goal 3, and our SN1, SN2, E1, E2 comparison. So that's going to be the summation of all of this week's work. And then we have the activity after the break, which will be assigning R&S in teams, okay? So, and then at the end of that, you'll go ahead and submit your final answers, and that's going to be your activity that we're going to do for points, okay? Any questions on that right now? Okay, let me go ahead and share my screen. Okay, so I hope everybody can see my screen there. Let me move the thing over here. Okay, and I think my Zoom chat is still working, so we have that as well. Okay, so in the last section here of goals, we looked at the nomenclature and properties of alcohols, ethers, and thiols. And we learned that alcohols have their major change because of the hydrogen bonding available to it, and those alcohols can act as acids or bases. Ethers don't hydrogen bond, but have dipole-dipole interactions, which changes their materials. And thiols, because the electronegativity between the sulfur and the hydrogen is so close, they don't hydrogen bond, but they do have acidic protons and are more acidic than alcohols because they are much larger, okay? This is chapter, yeah, I copied and pasted chapter 7 wrong. This is chapter 8. So it is chapter 8, alcohols and ethers, but it does say chapter 7 goals, but this is really chapter 8. So we learned about SN1, SN2, E1, E2 in the last chapter, but we actually can make alcohols and dehydrate alcohols to make elimination products and substitution products, which is why we're introducing them again here. We're reinforcing what we learned in the alkyl halides to give us our SN1, SN2 versus E1, E2, okay? So in the case of trying to convert alcohols to alkyl halides, we can do this in a couple different ways. And the first thing is, for example, if we're using a water-insoluble alcohol, which is one that has more than 5 carbons in it and only 1 alcohol, those tend to be insoluble in water because the hydrogen bonding can only pull in 4 or 5 carbons, okay? So we have to do this in a way such that we dissolve it in some other solvent and bubble in gaseous HCl. Notice this works really well for tertiary alcohols because we go through a carbocation intermediate and it makes it very easy to create these, okay? Now, this type of reaction works very poorly with primary and secondary alkyl halides. Notice we've changed the acid to HBr and HI. HCl is not strong enough to do this substitution in a primary or secondary, and we have to actually use a catalyst, but we're not going to talk about that. We're going to talk about using those really strong acids of HI and HBr, which actually do work. And they work because they go through a substitution reaction instead of a carbocation because they're primaries, okay? So let's look in that a little bit more detail. So if we're looking at that primary alkyl, that primary alcohol, and we're hitting it with an acid, okay? The first step in this SN2 reaction is to make a better leaving group. Remember, alcohol is not, OH minus, the hydroxide, is a poor leaving group because it's a very strong base, okay? So to make it a good leaving group, we use the acid portion of the HBr or HI to protonate the alcohol. Once we protonate the alcohol to get that oxonium ion, we now have a good leaving group because when, okay, come on. Oh, it's on that. When we create this oxonium cation here, when it leaves, it takes these electrons with it and it turns into neutral water. So the first step, and remember that's one of our patterns we look for in mechanism, is adding a proton. So then their second step in that is attack of the nucleophile, which in this case is the bromine. Because we use the hydrogen from the hydrogen bromide, it is now the bromide ion. It is now a good nucleophile and can come in and displace our neutral water, giving us two neutral compounds at the end of the reaction here, okay? So because it's a primary, we know it has to be an SN2 mechanism, because SN1 mechanisms require carbocation, and our primary carbocation is the worst carbocation possible, so it must undergo an SN2 type reaction. Okay. So in the case of the tertiary compound, what happens first is, of course, we get the addition of the proton. In the case of primaries, we had addition of the proton and then an SN2 reaction. In the case of the tertiaries, we still get that transfer of a proton to make a good leaving group. But because we can form a tertiary carbocation, the water then leaves first. We get the breaking of the bond to form that stable molecular ion to give us our carbocation. Remember, we cannot have an SN2 reaction with a tertiary because of sterics. So we protonate first. Again, water leaves as a neutral species, generating our carbocation, and then we have the final attack by the electrophile to form our new covalent bond. So primaries have to go SN2, but the first step is still protonation of the alcohol. Tertiaries can go SN1, but again, the first step is still protonation of the alcohol. Okay? So, oh, there's the first step. So that's the first step. And then the second, third steps are what we'd expect for a SN1 reaction with that carbocation intermediate. How did I mix those slides up? Oh, well. All right. So let's think about the overview of these. So that means that our primary alcohols, just like our primary alkyl halides, never form that carbocation and never do an SN1 type reaction. So we know that's an SN2 type reaction. Now, our tertiary alcohol, like our tertiary alkyl halides, creates that carbocation because it's a tertiary carbocation, which is most stable. Therefore, it's always SN1. However, once we get to the secondary alcohol, it's going to be a little different, and it can go either way depending on the strength of the acid. But the first step in any of these the reactions with HX with water with an alcohol will be the protonation of the alcohol. Okay, so that's SN1 and SN2 as far as alcohols go. Now let's look at E1 and E2. Previously, when we were looking at the elimination reactions, we typically used a base. And so in an E2 reaction, the base was pulling on the hydrogen so that the leaving group could leave to eliminate, okay? In the case of the dehydration of alcohols, we actually don't do it in the presence of a strong base because, again, hydroxide would be a bad leaving group. So we kind of flip it on its head again, and we do what we did before, where we protonate the alcohol to make it a good leaving group of water, okay? So in all of these dehydrations of alcohol, even though we're looking at beta eliminations, this is acid-catalyzed so that we are adding that acid to the alcohol to make it a better leaving group, okay? So primary alcohols are very difficult to do this with. You need very high temperatures and a very strong acid. Secondary alcohols are a little bit easier to do. And if we start thinking about the mechanism, we'll see why. And in tertiary alcohols, it actually doesn't require much higher temperatures, only slightly above room temperature. So just from those different descriptions here, we're going to start to think, okay, that tertiary alcohol is probably going to go an E1 reaction because it'll protonate and then turn into a carbocation and therefore be easier to leave. But let's double check to make sure that's happening here. Okay, so in an E1 mechanism, come on, share with me. There we go. In our E1 mechanism here, it of course has to be 3 steps. We have to form that carbocation in that E1 reaction. So the first step when we have an acid is to protonate the alcohol. So in the case here, we're going to use a secondary alcohol, and we are going to do our first thing is to protonate it to give us our oxonium ion here. Okay, that lets us go to our next step here. So in the case of our secondary alkyl halide, our secondary alcohol or our tertiary alcohol, the next step is the slow step, or the rate determining step, is the breaking the bond to form that secondary or tertiary carbocation and neutral water, okay? So now the generation of neutral water is important here because remember, water is a Lewis base. It's not a very strong base, but it's a Lewis base. And we now have that carbocation. The substrate is activated to have that hydrogen leave, take away our positive charge by having the electrons from the Lewis base attack the hydrogen to create our new sigma bond. The electrons that were holding that hydrogen on the compound now come in to give us our double bond, and we regenerate our acid catalyst here. Okay, so in the case of our secondary or tertiary, we're going to go through an E1 mechanism in carbocation. Okay, but it said before on the previous slide that it takes much higher heat to get a secondary alcohol to go than a tertiary alcohol. Tertiary alcohols go near room temperature, okay? And that has to do with the stability of our carbocation. Our secondary forms a secondary carbocation, which is less stable. So it takes a greater energy, more activation energy to get it up that hill to give us that secondary carbocation. That's why there's more heat required for our secondary than our tertiary, but it still undergoes the same mechanism of E1. Okay, so in the case of our primary alcohol, because we cannot form a primary carbocation, we must undergo the E2 elimination. But we're going to do exactly the same steps. We're going to protonate the alcohol first to make it a better leaving group. When we protonate that alcohol using our hydronium ion to get us our oxonium cation here, we now form water. Water acts as our Lewis base again. So our water is required to go out and start grabbing that hydrogen on that beta carbon. When it does that, it forms its new, regenerates that acid, and those electrons that were on that hydrogen kick in to give us our alkene, okay? And then when the electrons kick out from the oxonium cation, we regenerate our water. So the reaction continues to go again and again and again. Okay, because our primary alcohol can't form a primary carbocation because they aren't stable, it has to wait for water to act as the base. And water is a very poor base, so it takes much more heat to make it undergo that E2 reaction, okay? So let me go back and look at that thing here. So in the dehydration of alcohols, our primaries take high heat and a lot of acid catalyst, and it is undergoing an E2 reaction with water as our base, okay? For the secondary and tertiary, we get an E1 reaction with the secondary being less stable, so it takes more heat. And the E1 for the tertiary is easier because it forms a tertiary carbocation, okay? So just looking at that primary, secondary, tertiary, it reinforces everything we learned about elimination 1 and elimination 2 in those strong base situations we had in the previous slide. All right, last thing I want us to do is when we react these epoxies, these ethers, okay, all of these ethers actually undergo an SN2 reaction. Okay, so this is one of the few ethers that is very reactive, and it's reactive because of the ring strain. It forms that three-membered ring. It really wants to pop open. Okay, so it is very susceptible to a nucleophilic substitution reaction to make it ring open. But it's a bimolecular reaction. And we know this to be true because, number one, we can only form a secondary carbocation in the system. And so that's not very stable. Plus, whenever we do these reactions, we always get the addition of the nucleophile on the least substituted side of the material. So you'll notice here, I'm going to change colors to blue here. We're always going to attack by the nucleophile on the least substituted side. What that means is when this opens up, the alcohol that is formed when it opens up is always on the more substituted side. So let's go ahead and look at our products here. So the nucleophile had to be this nitrogen containing material here, our ammonia, and therefore the two hydrogens and the nitrogen end up on our beta carbon here, and the hydrogen here on our alcohol actually is the other hydrogen from our nucleophile, okay? So in the presence of water here, these are actually backwards. This is actually our beta carbon and this is our alpha carbon here. But it's really hard to tell the difference because they're both alcohols, okay? But if we were to do some experiment where we could prove one alcohol over the other, we would see that the nucleophile attacked on the least substituted carbon. And if we change that nucleophile to make it very obvious, go sulfur as our nucleophile instead, we again attack at the least substituted carbon. Okay, so what's that telling us is that we have SN1 and SN2 reactions happening in our alcohols as well, and we have E1 and E2 reactions happening in our alcohols as well. And it all has to do with whether it's your primary, secondary, or tertiary. It follows the same rules we had for these substitution reactions in alkyl halides. But in the alcohols, we have to use acid-catalyzed to make the OH a better leaving group. All right, I'm going to stop sharing right here. All right, questions on that, okay? So we're adding basically the same rules we had, we're adding to the same rules we had with the alkyl halides. It's just showing us that in alcohols, we do have to do that protonation to make it happen. Okay, question is there a way you could show the E reaction side by side with the S reaction? Okay, let's see. Remember, the E reaction is an elimination reaction. So we always go from an sp3 hybridized carbon to an sp2 hybridized carbon. And the substitution reactions go from an sp3 hybridized carbon to an sp3 hybridized carbon. We keep that substitution. So if I were to show that side by side, how would I do that? Let's see. I would try to go to, let me see about doing it here. I'm looking for a side-by-side example of E1, E2, SN1, SN2. And I don't seem to have a slide that does that. Okay, I have a little extra room on this slide, so let me go ahead and share this slide and I will draw them separately here. Okay, so if we're looking at SN1, SN2, what we're going to see here is that our SN1 and our SN2 is going to have the general structure of R, X, and that X could be a halogen or a protonated water, and it's going to go to an R with a sigma bond where that nucleophile attacked, okay? So both of these, this is the general reaction it'll go through, okay? Because all we're doing is displacing something that was on our long chain alkane, and we're taking it off and adding some other group there. So that's the generalized structure for the SN1, SN2 reaction. Now, in the E1, E2 reaction, so the generalized structure is a little different, where we have C, H, H, R, C, H, H, X. And in all of the E reactions, whether it goes through a carbocation or not, what happens is, let's change to red. One of these hydrogens is removed. These electrons kick in to form a double bond, and this electron kicks out to give us our final product. And so our product for these reactions are going to look like this: H, H, C, H, and R. So looking at the reactions side by side, SN1 and SN2, whether we form a carbocation or not, ends up with an sp3 hybridized sigma bond. All E reactions end up with an sp2 hybridized carbon plus a pi bond. Okay, does that answer your question? All right, great. Actually, that's a nice little review to tell us, you know, we've really come a long way in understanding what we've got. Okay, so I want to do, before we get, we have just enough time to finish our chapter 3, goal 8. Let me go ahead and share my screen. I'm sorry, chapter 8, goal 3. Okay, and that is the different reactions we have, okay? So in the different reactions we have here, what you should see is in these alcohol reactions, we have a certain things and they repeat a pattern, okay? In the ether reactions, we only have one reaction of ethers. In the thiols, we're only going to take about one reaction of the thiols, okay? So what we're looking for is not that, oh, these are all different reactions. We're looking for the similarities between these reactions, okay? So the first thing we have is we have a taking of the alcohol and turning it into a salt. Now, when we do this, we can do it with a very strong base. The problem is then we have to remove the other thing. We either have to remove water or some other salt from the system, and it's very difficult. So what we do instead is we take a reactive metal, sodium, potassium, lithium, and we actually end up oxidizing it, stealing electrons away from it, turning it into a positive charge. When we do that, the hydrogens accept those electrons, become reduced, and go away as hydrogen gas. So this one is number one, and what we call a redox reaction, a reduction oxidation reaction. But the other thing we do is notice that that methoxide, that's one of our nucleophiles, and that's one of our really strong bases. So this is a reaction we use for alcohols to actually make it into other things, okay? So something like this can be used a lot as a nucleophile on primary alkyl halides, but it's also a good base for, in secondary and tertiary alkyl halides, we'll end up with beta elimination, okay? So that's one kind of reaction alcohols do. Okay, the next kind of reaction they do is they can remove the OH and go back to an alkyl halide. Remember, that's one of the reactions we did in alkyl halides is we reacted with hydroxide to turn it into an alcohol from an alkyl halide. Here we can use an acid to displace the OH and turn it back into an acid chloride. I'm sorry, an alkyl chloride. Okay, so they undergo different mechanisms based on whether you have primary, secondary, or tertiary, and of course, whether or not they go through the carbocation is based on that stability, okay? Notice that in the case of these really low molecular weight alcohols, are unreactive in this condition, okay? And that's because this low temperature addition goes through a stable carbocation. You cannot get stable primary or secondary alcohols without a lot of activation energy. You have to really heat them up to go up that energy scale, okay? So because they don't go through with HCl, we have to do different things for those other ones. In fact, the primary alkyl halides we cannot create from an alcohol without using a special reagent. And our special reagent for that is thionyl chloride. Now, the reason this works is OH is not our leading group here. It actually turns out there's a sulfur oxygen compound that is our leaving group, okay? Don't worry about the mechanism, but the idea is that we're creating a sulfur oxygen bond, and that becomes our leaving group so that it can be displaced by the chloride. We are not forming an OH minus as our leaving group. We're forming an OSO minus leaving group. Okay, that's why it works. And so that's why we can take our primary and secondary alcohols and turn them into alkyl chlorides, where we couldn't do it with HCl because chlorine is not a strong enough nucleophile to do that, okay? And of course, because of primary, secondary, we see that there are, the mechanism is determined by what that intermediate might be. So because primary alcohols can't form primary carbocations, we have to go with an SN2 reaction. Because tertiary alcohols easily form carbocations, they will go through an SN1 mechanism. And secondary alcohols can do a little bit of each depending on the strength of the nucleophile. Now, what I want to note here is that when we have a chlorine on there, we undergo that SN2 reaction. For bromine and iodine, it's more likely to give us our SN1 reaction. And that is evidenced by this reaction here with the thionyl chloride on our primary and secondary alkyl chlorides. Okay, so the next thing we have is our elimination reactions, our E1 and E2 reactions. These are E1 and E2. And it all depends on whether it's primary, secondary, or tertiary alcohol. So obviously this would undergo an E2 reaction because it's primary. This is going to undergo an E1. This is going to undergo an E1. So we can form carbocations. And they're acid-catalyzed. The first thing that happens is you protonate that alcohol. Then an alcohol will leave as the water. And whether or not the water itself is being used as the base or not is the difference between the E2 reaction. The water in the solution is acting as the base to allow that E2 reaction. In this case, we're actually forming our carbocations, and the E1 mechanism rules for these. But it's the same basic mechanism. It's just an elimination reaction instead of that substitution reaction. Okay. So the next thing we learned about alcohols is that there are two hydrogens right here. Okay, and so by removing a hydrogen from one of the carbons and a hydrogen from the alcohol, we can generate this new carbonyl group. Okay, and in the case of things that are very strong oxidizers, it doesn't stop here. It actually oxidizes off this hydrogen too. But when we take our chromic acid, our CrO3 here, and we react it with HCl and pyridine, we create this new complex, this PCC. And this PCC oxidizes alcohols, but it's not too strong. Therefore, we can stop at the aldehyde. It's the only reagent we have so far that'll stop an oxidation halfway to the carboxylic acid. So remember, if you want an aldehyde, you have to use PCC, okay? But if you don't care to stop there, you can use the stronger chromic acids, which I don't have on your slide, and they will convert primary alcohols to carboxylic acids. They will convert secondary alcohols to ketones, and tertiary alcohols are not reactive with either of these reagents. Okay, so that's the key there, is that the tertiary alcohols, and the reason is they don't have a hydrogen on the carbon that the alcohol's on to take away. Because there's no hydrogen to take away, you're not going to break a carbon-carbon bond to do this, so they don't react. Okay, so our only reaction on ethers we want to talk about is this ring opening reaction of ether and how we make it. So the key to the thing is this three-membered ring, and the three-membered ring is really, it wants to be 109 degrees, you're forcing it to be 60 degrees. That difference in angle is ring strain, and it wants to pop open, okay? So we can generate this by just oxidizing a double bond and adding an oxygen to it. That's one way to make it. But the more important reaction is actually also to use what we call a per acid, okay? The reason we call it a per oxy acid is it has one extra oxygen in here. Remember, carboxylic acid only has 2 oxygens there. And so because we have an oxygen bond, that's a nonpolar bond. That makes this a very reactive species, and that's how we can generate that epoxy compound. And then of course, the epoxides, their number one reaction is to ring open. When it's attacked by a nucleophile, it'll attack on the least substituted side and open the ring up. Notice, because it's on the least substituted side, we can actually see the ring opening is an anti-addition in these ring systems, this 5-membered ring system. We don't see that in the linear system because we have free rotation. Here in the ring, we actually see it is actually an anti-addition. The nucleophile attacks on the backside on the least substituted carbon to ring open and give us our product. Okay, and there's the mechanism, of course. And again, when we have these attacks, they attack on the least substituted side, and so we generate an alcohol and the nucleophile on the one carbon over. And so we get this nice 2 functional groups for the price of 1 reaction. That's one of the really cool things, because when we did just substitution reactions, we converted 1 functional group to another. When we did those alcohols, we took the OH and made it into an alkene or something else. Here we actually get 2 different functional groups for that 1 reaction. And that's one of those neat things about these epoxy reactions. Okay, all right. Okay, so what we can do here is then, using that ring opening system, we can actually create these kind of substructures right here, where we can actually attack an epoxy structure with a nucleophile, like nitrogen with 2 ethyl groups hanging off of it, and generate these longer building blocks from a very small 2-carbon chain. Okay, can you please review how to determine the least substituted? Okay, that's a good question. Okay, so let's go and look at this from a steric perspective. So we're looking at it from the idea of, I'm a nucleophile, I'm going to come in and attack this molecule here. If we look here, we have 2 hydrogens on this side. We have 1 hydrogen on this side and 1 methyl group. Methyl groups are much larger than hydrogens, okay? So that means this is our more substituted side because it takes up more space, okay? So if you had 1 methyl group and 1 hydrogen and 2 hydrogens on this side, this is the least substituted side, okay? Now we can actually go where sometimes we'll have a carbon-carbon with a CH3, CH3 with our epoxy here, and there's hydrogens over here. Again, where the hydrogens are, the more hydrogens you have is the least substituted carbon. Remember, when we talk about primary, secondary, and tertiary carbons, the increasing number is the increasing number of carbon-carbon bonds. Okay, does that answer your question?
Yes, it does. But so you said the most hydrogens equals the most or the least,
The least substitute.
unless it's a methyl group.
Okay, well, no, but the methyl group counts. The carbon-carbon bond here, we're looking at the number of carbon bonds. The fewer number of carbon-carbon bonds you have, the less substitute it is. Okay, because
Okay.
when you have just your methyl group here, okay, then we have no carbon-carbon bonds, and that's what we call our methyl. And if we had one carbon-carbon bond, that's what we would call our primary, right? Because it only has one carbon-carbon bond. And then if we had two carbon-carbon bonds, it's secondary, 3 is tertiary, and 4 is quaternary, okay? So the higher the number, the more substituted it is, okay?
Okay, thank you.
All right, and so the only reaction we have with thiols is what we call the oxidation of thiols to form a disulfide. So basically you are literally changing the oxidation state to create a sulfur-sulfur bond. And this sulfur-sulfur bond is used a lot in proteins. It's used a lot in tires, okay? So this is the only thiol reaction we have that we use here. And if you do take the follow-on course, which is Introduction to Biochemistry, you will see this bond used a lot, okay? Okay, so that is the last thing I want to show you about the goal 3 of chapter 8. That's chapter 8, reactions. And so those are the primary reactions we have with alcohols, the most important reactions we have with ethers, and the only reaction we have with thiols. Okay? Okay, I'm going to stop sharing now. I'm going to go ahead and stop recording and go ahead and post this as soon as it's done processing. Let's meet back here in 10 minutes at 12:50, well, 8 minutes. Yeah, no, 12:55. Let's meet back at 12:55 and we'll do the group thing, the group project. If you were able to print that sheet up, great, have it in front of you. If you weren't able to print that sheet up, go ahead and have a blank piece of paper in front of you so you can draw it. So that, and at the end of this, we're gonna go ahead and take a picture and we're gonna submit it to your Dropbox in tracks. So go ahead and either have that printed up or have a blank sheet of paper for you to write the answers on, okay? And we'll see you back here at, okay, 12:55. Let's go ahead and have a long bio break.